In this video, we're going to look at encapsulation, which is the first important way that we're going to use local. Encapsulation is one of the most fundamental concepts in software engineering, and this is what it's about. Imagine a large software system with 10, 20, 50, or 100 programmers on it. Now ask yourself, how likely is it in that situation that two programmers are going to want to use the same function name for two completely different functions? It's pretty likely, right? It's almost guaranteed to happen, in fact. And that's the problem that encapsulation solves. What encapsulation lets us do is to take each part of our program and make it into a capsule, a little package that has a bunch of internal functions and constants and structures, and only a small number of external functions and constants and structures. What encapsulation rests on, and I'll explain why we call it encapsulation as we go, but what encapsulation rests on is the observation that with a local, the A and the B, in this example, don't exist out here. If we draw the scope contour, that A and B don't exist out here. Now, why would that be useful? Well, let's go to FSV4, which is the file system example we did last time. Now, when we designed the functions in this file, because we had mutually referential types, we always ended up with two functions with these kind of silly names. There was some data element and some data LOE. And really, from the perspective of someone who's holding on to an element and wants to sum all the data, they don't care that there's two functions. They really only want one function, and they would like it not to have this silly name. But the function they want to call some data has to have this helper. So how can we fix that with local? Well, watch this. I'm going to do it once quickly, and then I'll come back and do it slowly. What I'm going to do is I'm going to say, really, the function that the rest of the world wants to call is a single function that operates on an element. So I'm going to give the rest of the world a single function that operates on an element. And I'm going to put the two functions I wrote before as locally defined functions. I'll press Command-I to fix my indentation. So now the two functions I originally defined are in there. I got to go change the name of all these tests. I got to get rid of this test because some data LOE is not available at top level anymore. I have to switch to intermediate student language because I'm using local. And let's try it. That function's now running. Now, several things are different here. I'll redo the process in a minute with another example, but several things are different here, and let me talk about them. The first and most important is that the two mutually recursive functions, the ones with the funny names, are now encapsulated. They're wrapped up inside this local, and nobody outside the local can see them. As far as the top-level program is concerned, the only function that exists is some data. Some data encapsulates some data-element and some data-LOE. So that's the first difference. The mutually recursive functions are encapsulated. We only see a single global function. Because of that, I'm only publishing one signature, the signature of some data. Because of that, I have fewer tests, because some data is the only top-level function. Now, in the encapsulation mechanism provided by industrial strength languages, you would still be able to write unit tests for encapsulated functions. The fact that we can't write unit tests for encapsulated functions here is just to keep check expect simple. Being able to write unit tests for encapsulated functions introduces a number of complexities that aren't really interesting for us for now. So those are some observational differences. How's this thing working? When we call some data, for example with F1, so we call some data, we evaluate the local, all the renaming and lifting happens, and then the body of the local calls some data dash dash element. And then that calls some data dash dash LOE and back and forth until it gets the result that's produced by the body in the function. Sometimes we call this line here a trampoline, because what happens is we come into the top of some data, bounce off the trampoline into the mutually recursive functions. Boing. It's a silly name, a trampoline. I think you've got the idea pretty well by now that computer scientists like silly names. The more, the better. So there we go. That's a first example of encapsulation. Now what I'm going to do again is to do the process of converting multiple functions into a single function with encapsulation more slowly. I'll work through the process more slowly, telling you what each step is, and then I'll leave you to do the third example on your own. So let's go down here to this next one. The first thing is to identify some functions that are a good candidate for encapsulation. And what makes these functions a good candidate for encapsulation is that there's two or more functions that work together. Another way of saying it is that there's one function that has one or more helper functions, and the rest of the program really only wants to call one function. In this case, all names operating on an element is really the only function that the rest of the program wants to call. All names dash LOE is just a helper for all names dash element. So the first thing is to identify a candidate that has this property, that there's a function with one or more helpers, and the rest of the world really only wants to call one function. The next thing to do is to think of a name for the function that the whole world will call. Sometimes one of the functions already has that name, sometimes it doesn't. In this case, I think all names dash dash element is a lousy name for the rest of the world to use, so I'm going to make up a new name. So I put the function header like that. Then I say local and an opening square bracket, and I go after the last of the functions and I close the square bracket. I'm not going to fix the indentation yet. I will in just a second. And then I write a trampoline that calls the appropriate one of the multiple functions to get things started. I close all the parentheses. I type Command-I to fix the indentation. So now I've done the encapsulation. I just have to clean up the paperwork. First thing I have to do is, if there were multiple signatures, now there's really only one. Now there's just the signature of the function that the whole world sees. So I'll get rid of the second signature, and I'm going to clean up the tests. Oftentimes this is going to mean getting rid of the base level test, and I'll talk about the implications of that in a minute. I'm going to first get rid of the tests for the function that we don't have anymore. Then I will do a renaming of all the other tests. I'm going to copy that. I'll say find, come down here, find that, replace it with that. I'll say replace. These stubs, there's two choices now. I could do that replace and get rid of the second stub, get rid of that S. That might be one thing to do. Or you could just delete the stubs entirely. And now, of course, whenever you do something like this, you test right away to make sure you didn't mess up. And I didn't mess up. Now, the way I did that process so methodically follows this notion of a refactoring. The idea of a refactoring is you're going to make a change to a program that doesn't change its behavior at all, It just changes its structure. Sometimes you want to do a refactoring and then change the behavior. You should avoid the temptation to do both of those at the same time. First do the refactoring, check and test that the behavior is still correct, then change the behavior, right? Move in small steps. So there we go, that's a second example. I'm going to come back to talk about the fact that we deleted the base case test in a minute. But first, I'm going to leave you to do an exercise, which is to go ahead and do the encapsulation of the find functions in the way that I've just done. So have this starter in front of you. You should have had it in front of you all along, and you should have been doing this all along. But I'd like you to go ahead and do this one now for yourself, just to practice the whole step-by-step process I did. And to help you, I'm going to put the steps of the process back on the screen, and you can also find them in the design recipes on the Using Local for Encapsulation link. So there's my solution. I basically just followed that process. I called the top level function find, and I removed one signature, I removed some tests, I renamed the function in the tests, I did the encapsulation, I did the whole thing, and there we go. All tests pass. Now, we just did this for all three of the functions operating on this arbitrary arity tree. And we also know that for functions operating on mutually referential types, there's always going to be multiple functions. They're always going to go together. So that might give you an idea about the template. It gives me an idea about the template, and here's the idea it gives me, which is maybe what I should do is pre-encapsulate the templates. Maybe I should make a function like this. Maybe I should write the template like this. Define fun for element E local, and then both of these template functions. Get rid of this comment here. And now I have a pre-encapsulated template. You could do that. It would work out pretty nicely, actually. Let's see what the consequences of having that template are. Let's copy that template. And let's go back down to, for example, some data, and pretend for a minute that we don't have the solution. Pretend that we're just at the copy template stage. I've now just copied the template. Well, what am I going to do? I have to rename the template. Notice I don't have to bother to rename the internal functions. The rest of the world isn't going to see those internal functions. So they could be called strawberry and banana for all the rest of the program cares. It's perfectly fine for them to be called fun for element and fun for LOE. I don't have to rename them at all. And now I just code to the examples. Let's see, if I'm summing the data, I don't care about the name. I'm going to add the data of this element together with the natural mutual recursion. The base case result is 0, and in the combination step here, I also put a plus. And I'll run it. And here I very, very quickly got to the encapsulated solution. It's almost exactly the same as this encapsulated solution. It's just that here the inner functions, the encapsulated functions, still have their template name rather than having a custom name. But as I've said, that doesn't matter. What's the advantage of doing it this way rather than starting with separated templates? Well, the big disadvantage of doing it this way is that I wasn't able to have a base case test during development, because I'm not able to write a test for just the LOE function. I have to write a test for the whole function. So here's what I would say about that. At this point in the course, it's still important to have unit tests. It's always important to have unit tests. And the basic idea of testing simple cases first is always important. But you're getting sophisticated enough now that you may not need to actually have the absolute base case test first. It might be enough for you to have a simple test first, a test that's kind of one away from the base case. And if that's true for you, then you can go ahead and design a function like SumData using pre-encapsulated templates. If you're not comfortable with that idea, if that gives you the willies, then don't start with pre-encapsulated templates. Start with separate templates, start with the full set of unit tests with base case tests and everything, and then once your program works, encapsulate it. That's fine. For that matter, you don't absolutely have to encapsulate it, but let me tell you why encapsulation matters. Remember what I said, cars have 8 million lines of code in them. In 8 million lines of code, how likely do you think it is that two different programmers once wanted to use the same function name? Is it 99% likely or 100% likely? It's one of those two. And that's what encapsulation does. It lets one programmer have a whole bunch of functions with whatever names they want, and they just publish to the rest of the world a small number of functions with really good names. All of their internal functions are totally hidden. And that lets them do what's called namespace management. It lets them deal with this naming problem. And it also makes sure that other programmers don't call functions that they're not supposed to. You know about the toHttp image library. And really what's going on when you say require toHttp/image is what you're saying is you're talking to the encapsulation mechanism built into Racket. And you're saying, hey, grab the whole whack of stuff that's the toHttp image library and let me see only the published names. There's also going to be a lot of unpublished names. As a general rule, when you grab a module of code, there's far more unpublished or hidden names than published names. And that's what a require mechanism is letting you do, is it's letting you say, just let me see the public names, leave all the other ones encapsulated. So there you go. That's the first use of local, which is to support encapsulation in the teaching languages. Other languages have more sophisticated encapsulation mechanisms, but the basic idea is always the same. Take two or more functions, hide all the helpers inside a capsule so that the rest of the world sees only the functions that are really appropriate for the rest of the world to call.